holes collide. New simulations uncover the secrets of OJ287. In a groundbreaking discovery, researchers at the Canadian Institute for Theoretical Astrophysics, CITA, have used advanced simulations to unravel the mysteries of the OJ287 galaxy, located a staggering 3.5 billion light-years away from Earth. This galaxy showcases extraordinary light bursts, equivalent to the brilliance of 1 trillion suns, approximately every 12 years. These phenomena are now attributed to a binary system of supermassive black holes. The secondary black hole, with a mass of approximately 150 million solar masses, repeatedly passes through the disk of gas surrounding the primary black hole, which has a mass of around 18 billion solar masses. This interaction disrupts the gas disk structure, generating outflows and intense bursts of light. Sean Ressler, a postdoctoral researcher at CITA, led a study presenting the first comprehensive simulations of OJ287. The research, co-authored by Luciano Combi, Bart Ripperda and Xinyu Li, delved into the complex interactions between gravity, electromagnetism and fluid dynamics associated with these black hole collisions. Our simulations take into account the intricate dance between extreme gravity, electrodynamics, and fluid dynamics to rigorously test the model's ability to explain the observed outbursts, Combi explained. This is a significant advancement, as it's the first time we've simulated the entire gas disk around the binary black hole together. The team's findings provide compelling evidence that collisions within the disk produce sufficient energy to explain the observed bursts. These collisions also create disturbances that warp the disk and form spiral patterns. Ressler emphasized the importance of these calculations as a starting point for more realistic simulations. We've made a crucial step towards a fully coherent picture of the system, Ressler stated. However, we still need to incorporate the effects of how light is produced and then bent by the extreme gravity of the black holes. We've made some simplifications for now, but we aim to remove them and account for light's behavior in the future. The research also highlights connections to gravitational waves. The intense gravity from these massive black holes generates space-time ripples, which may be detectable by future pulsar timing arrays. Combining gravitational wave data with traditional telescope findings will significantly enhance our understanding of galaxy mergers, black hole physics, and cosmic growth. Ripperda added, by merging gravitational wave data with traditional telescope observations, we can unlock major breakthroughs in our comprehension of gravity, black holes, and the evolution of galaxies over time. Realistic simulations will play a pivotal role in predicting electromagnetic signatures from the plasma physics near the event horizon. The study, titled Black Hole Collisions with Thin Accretion Disks, OJ287 and Small Mass Ratio Supermassive Black Hole Binary Candidates, is available on arXiv. https://www.arXiv.org/abs/2509. For more information, visit the Canadian Institute for Theoretical Astrophysics, www.cita, and explore our understanding of time and space. https://www.spacedaily.com.html. Copyright 1995 to 2024. Space Media Network. All rights reserved. Our privacy policy, https://spacedaily.com/privacy.html. And GDPR statement, https://gdpr.html. Provide further details on our About Us page, https://spacedaily.com/whoweare.